Okay, so good morning. Today we'll begin chapter 2, and we'll talk about intrinsic semiconductors at the beginning. And then later on in the chapter, we'll talk about how we can create more charge carriers inside a semiconductor material. So for now, let's begin with the introduction to chapter 2. And let's see. Oh. Oh. Okay, solid state electronics. All right, so we'll begin first with a broad classification of materials, right? There's a material property called resistivity that we use to define three classes of material, broad classification in terms of electrical conductivity, meaning the ability of a material to be able to conduct electricity. In this case, conducting electricity would mean movement of electrons. Okay, when electrons move through a material, we say that current is flowing, energy is being transferred, they are carrying charge. So they are labeled as charge carriers. So depending on the resistivity, we classify them as conductors, insulators, or semiconductors. Okay, resistivity is noted by the Greek letter rho, R-H-O. And it has units of ohm centimeter, ohm times centimeter. You could say ohm times meter, but since you are working with small scale devices, typically tend to use centimeter for standard unit measurements. Okay, so resistivity is a material property, values for which are already known to us. Okay, so there are tables that have been published over the past several decades where you can simply look up a material and you can determine the resistivity of that material. You may have studied this in physics and may also have studied this in circuits 113. You can create a resistor from any material based on this equation, which is rho L over A. Does it look familiar? Right. So if you have a material, some length and some cross-sectional area, and I'm simply drawing a cylinder right now, but it could be any shape. This would be the length of the material. And this here is the cross-sectional area. So resistance of or resistance created from a material or a piece of material can be defined by this equation, rho L over A. It is directly proportional to the length, meaning the longer a piece of material, or longer the higher the resistance, the shorter or smaller the piece of material, the lower the resistance. And of course, cross-sectional area. And then of course, units for R are simply ohms, right? So three different classifications. The values are approximately 10 raised to 5, less than 10 raised to minus 3. And semiconductor materials have resistivity that is somewhere in the middle. It's between 10 raised to minus 3 and 10 raised to 5. So if the resistivity of a material is greater than 10 raised to 5 ohm centimeter, then we classify them as insulators. If it's less than 10 raised to minus 3, then we classify them as conductors. And if it's anywhere somewhere in between, then they are semiconductors. Okay. And of course, since this is a course, a class about semiconductor device fundamentals, these are the materials of interest. And as we go along in this chapter, I'll also explain that resistivity is not the only criteria for being called a semiconductor. Okay, there's something else also. All right, any questions so far? Right. Okay. So here is from column 2 to column 6 of the periodic table. Now, let's see. Okay. So column 2 to column 6 of the periodic table. We have our common elements here. You might be familiar with definitely the center of the periodic table. Semiconductors are elements that have 4 valence electrons in their outermost shell. Okay. To give you a broad overview, and before we get into the details, what we're going to do in this chapter. Semiconductors, as I stated, semiconductor materials are typically from column 4 of the periodic table, meaning they have 4 electrons in their outermost shell. So every atom that you see in column 4 is carbon, silicon, germanium. All of those have 4 electrons in the outermost shell. You require 8 to form a nice stable covalent bond. So if you have a silicon atom, let's take example, silicon crystalline structure, okay? You have silicon atoms that make connection and form bonds with surrounding silicon atoms, okay? Depending on the kind of bond it makes, you have studied probably covalent bonds, ionic bonds. So in a stable silicon structure, you have a silicon atom that creates bonds with 4 other silicon atoms. So each atom of silicon shares 1 electron with 4 of its neighboring atoms, thus creating 8 electrons in the outermost shell, the valence shell. And this is known as a covalent bond model. Okay, and again, we'll look at all of these in the next few slides. What happens is we begin the discussion at, let's say, 0 Kelvin, which is absolute 0, minus 273 degrees C. Okay, absolute 0. So at 0 Kelvin, everything is frozen solid. There is no energy from any of the bonds. Okay, and that is where we'll begin. Okay, so if you have a silicon atom, or a germanium for that matter, at absolute 0, all of the electrons in that atom are in place. They're all forming a bond with each of their neighboring atoms. For most of this class, all of our examples will be just based on silicon. Okay, that is the most common semiconductor material, and that is where our focus will be. Okay, so if we begin with silicon, we call these as intrinsic semiconductors. Right now, let's say we are at 0 Kelvin. Okay, at 0 Kelvin, everything is in place. Everything is frozen and in place. There are no free electrons to move around. If there is no movement, there is no charge flow, and there's no charge flow, there is no current. Okay, so these are known as intrinsic semiconductors. Now let's put a pin in the 0 Kelvin for just a minute, and then we talk about compound semiconductors. Okay, so to the left of carbon, silicon, germanium, we have column 3 elements, and to the right we have column 5 elements. It is possible to create a compound with 1 element from 3 and 1 element from 5 to create a compound semiconductor. And you create a compound semiconductor, we call them So compound semiconductor. And you can create them with 2 elements. We can create them with 3 elements. We can also create them with 4 elements. Okay, so depending on how many elements we use, we have a different name for each one of those. For instance, we could create a compound semiconductor with gallium and arsenide. And gallium arsenide. You can also create by combining gallium and nitrogen to create gallium nitride, which is now very popular and very common in fast chargers. Mobile fast chargers, if you've seen commercially available, they will say we are using gallium nitride technology. It's basically some of the devices in there are created using gallium nitride. And then we can also create, so these are examples of column 3, 4. So these are referred to as, sorry, not 4, 5. 3, 5 compound semiconductor. Okay, because we chose an element from column 3, another from column 5. So these are known as column 3, 5, or simply 3, 5 semiconductors. We can also create from column 2 and column 6. And so these would be known as 2, 6 semiconductors. Column 2, 6 semiconductors. In both examples, you would see that the number of electrons in the outermost orbit would be 8. Okay. So this is very familiar, right? Everybody is familiar with the Bohr's model. It was then modified into the Rutherford model. So there have been several models, over the past, centuries, but this is the most common one. The nucleus, which have the protons and the neutrons, and you have the orbiting electrons, and these electrons are free to move, meaning they could leave that atom and are free to carry charge from point to point inside the material. Okay, they leave behind ionized atoms inside the material. Now, in these models, what is stated is that the electrons cannot occupy different orbits or different energy levels at random. The energy levels are quantized. So every orbit has a specific energy level. Every energy level is quantized, meaning it has a value. And electrons in a particular orbit will all have the same energy. And these energy levels are, again, there are discrete energy levels. They are quantized with a specific value. An electron can acquire sufficient energy to move up or move down. And it could also acquire enough or sufficient energy to break a bond and leave the atom. And that is where our semiconductor electronics comes into the picture. If the electrons are free to move about, we can impart enough energy, or we can introduce enough free electrons in there to create extra charge carriers. Again, if an electron can break free of a bond and be available to move around, that means it can conduct electricity, right? So we can impart either energy, or we can create enough free electrons via some other methods. And creating free electrons in there in a material by introducing from some other method, that is the primary foundation of all semiconductor devices today. Okay. So this is a illustration of a typical silicon lattice structure. Inside a silicon piece of material, all the electrons are arranged in a specific formation. This formation is known as a unit cell. So here, we are showing you one silicon lattice unit cell where each silicon atom is connected to 4 other atoms, which is more clearly illustrated right here. So each one is bonded with 4 neighboring atoms. And each one of those silicon atoms shares 1 electron each. So it forms a covalent bond. Okay. At absolute zero, all of these bonds are in place. All of the electrons are in place. As the temperature rises from 0 Kelvin, it goes up to like 10, 20, 30, 40, 50, 60, 100 Kelvin, 200 Kelvin. Now, this is still below zero, like the zero that we, what we call it as freezing temperatures, right? So minus 273 degrees C. It's coming up. But compared to 0 Kelvin, thermal energy is now being acquired by these electrons. And when thermal energy is being acquired by these electrons, as it gets up to room temperature, that material, the silicon material, has acquired enough sufficient energy that some electrons are able to break free of their bonds and are now free to move around the silicon lattice structure. Does that make sense? At 0 Kelvin, meaning minus 273 degrees C, everything is frozen, everything is in place. There is no free electrons to move around. As the temperature rises and comes up to room temperature typically is defined as 300 Kelvin or 27 degrees C. 27 degrees C is approximately 54, 32, about 85, 84, 85 Fahrenheit. Okay, that would be room temperature. So at that temperature, we say that the electrons have acquired thermal energy. When they acquire this thermal energy, they are able to break free of their bonds. Not all of them, some of them. Some of the electrons are able to break free of their bonds, and they are free to leave their atom and are now freely available to conduct charge. So these bonds that you see, which illustrate 1 electron being shared, can be broken. Okay, can be broken. And so each of these lines, I like to state that this is 1 electron and this is another electron. Because if atom A is sharing 1 electron here, let's say this is A, and this electron is shared by B. Make sense? Each atom is sharing 1 electron with its neighboring atom. And so there are 4 plus 4 electrons, 8 electrons. And one of those electrons can break free of their bonds and is now available to conduct electricity. So these free electrons are available to conduct electricity. The number of these electrons is far less than what would be in a conductor. It's higher than what would be in an insulator, but it's far less than what it would be in a conductor. Okay, hence a semiconductor. All right, let's take a pause. Think over that and let me know if you have any question. Yes. It's a different energy level. And they would move, yes. Mm-hmm. It's a question being asked, yes. Yeah, go ahead. Yes, that's in the future. 2 slides in the future, but it's there. Okay, so the first question that was being asked was, what does it mean by an electron breaks its bond, right? Or acquires enough energy? So the answer to that is, yes, it does acquire enough energy that it can now move in response to an external applied electric field. And the second question was about if an electron moves out of its spot, does it leave behind an empty space? Does it leave behind a hole? And the answer is yes, which we'll see in the next few slides. All right, other questions? Okay. So I just mentioned how semiconductors are between insulators and they are between conductors, right? Insulators have very few electrons available for conducting electricity. Conductors have a large number of free electrons, and semiconductors are somewhere in the middle. So if we want to convert a semiconductor into a conductor, we either impart enough energy to that material that more and more electrons are generated from thermal energy, but there's again an upper limit on that, or we introduce external electrons into our material. Introducing external electrons into our material is the foundation of everything that we're learning today. So here is a silicon lattice structure. This is a two-dimensional illustration. And here you can see all of these are shared electrons. So these tiny dots are shared electrons. And I'm just labeling the ones for the atom in the center. Okay, so each atom is sharing one electron with 4 neighboring atoms. Now you see the ordered structure of these atoms inside the material, right? If the silicon atoms are ordered and the order is repeated in the exact same manner, in the exact same fashion throughout the entire material, then we say that the material is single crystalline or single crystal. Okay. So it's the same order of arrangement throughout the structure. So if it's an ordered arrangement and the same arrangement is repeated over the entire structure, then we call it a crystalline material. We also call it as a single crystal material. The reason for that is if you have, let's say, a piece of material, and that piece of material, let's say, has 9 atoms right here. Okay. So you know the properties of these, you know the properties of these atoms, you know the properties of that piece of material. If it's the exact same structure throughout the entire material, doesn't matter how big or small it is, we can easily predict how that material is going to behave, because if it behaves in an X manner in one spot, it's going to behave in the exact same manner in a different spot. So we can predict how that material is going to behave. Single crystal material. Polycrystalline, as the name suggests, has multiple segments. So each of these is arranged in an order, but it has no long range order. Okay, no long range order. So it's in ordered segments. So it is not repeated. It's repeated for a small portion, but after a certain depth or a certain length, the order would change. So with different segments of order within inside the material. So multiple crystalline structures inside the same material, hence polycrystalline. And amorphous is basically no order at all. No order in the structure, hence an amorphous material. When we work with semiconductor devices, when you first begin, we always use single crystal silicon wafers. And they are, the technology has been around for several decades now. And so we are at the point where you can buy, if you buy a big box of silicon wafers, each wafer can be about $25, $30 each, which seems seems rather high, but in fact is very, very low. Because on one 4-inch silicon wafer, you can create hundreds of devices. Okay. Let's see, how much time do we have? A few minutes. So the other, let's see, energy band. Yeah, we have time to do energy band. So the first classification was the resistivity, right? We talked about resistivity, and then I pointed out that column 4 elements have 4 electrons in their outermost orbit. They form a covalent bond with neighboring atoms, which is nice and stable. Now, all column 4 elements are not semiconductors. If you notice, if you go back to this table, carbon by itself is not a semiconductor, even though it is from column 4. Okay, we can create a semiconductor using silicon and carbon called silicon carbide, but carbon by itself is not. And the reason is the energy band structure or the energy band gap. The electrons in a material occupy certain energy levels, right? We talked about discrete energy levels. In a conductor, what we call as the valence band and the conduction band energies overlap, meaning there are always free electrons with enough energy that they're free to move around. We don't need to impart any external energy sources on there. Okay, they're already there, they're available because the electrons occupy the valence and the conduction bands at the same time, meaning the electrons always have sufficient energy. In an insulating material, the valence energy level and the conduction energy level, and this is known as the energy band gap, or band gap energy. Okay, the difference between the conduction energy levels and the valence energy levels is known as the energy band gap or the band gap. It's a band gap energy noted by EG. Okay, in an insulator, that energy band gap is very large. In a semiconductor, the gap is present. It is not overlapping as in a conductor, but it can be overcome. Okay, it can be overcome. I'm almost out of time. We'll just go into this table right here. And this is the reason why carbon cannot be used as a semiconductor. The band gap energy for silicon and germanium is right here, so it can be overcome. This is not possible by all known laws of physics and unknown laws of nature. That energy band gap cannot be overcome. Carbon's energy band gap is almost 5.5 electron volts. So we cannot in any shape, form, or manner impart enough energy to carbon atoms that the electrons will break free of their bonds. Okay, that's why we cannot use it as a semiconductor material. So we'll end class here today. There's an extra credit reading assignment on chapter 2. It's not split up right now. It's the entire chapter, and I think students have already begun reading it. So as we go along in this chapter, please look up the relevant sections in the textbook. At this time, I think everybody should have access to the textbook and go along reading as we cover the material in class. Okay, we'll end class here today, and I will see you all on Wednesday.